Assalamualaikum. My name is Arnana binti Abdul Rahman, metric number DE220101. So we are from section 2 group 4. We'll be presenting our power system analysis project, which is impact of wind turbines on load flow stability. Before that, I would like to introduce our group member. So our group members is me, Irene binti Abdul Rahman, Nur Syafika binti Sulaiman, Kuhan anak lelaki Mani Rajan, Muhammad Nazrin and Muhammad Firdaus bin Faisal. The introduction of our project is there has been an increasing amount of global demand for electricity coupled with increasing number of concern over the greenhouse carbon emissions worldwide. There are a lot of renewable energy, but wind energy is one of the most stand out due to its environmental benefits and cost saving. Due to the environmental conditions, wind power generation system can lead to voltage fluctuations. This project aims to identify and analyze the wind power system operating condition based on the appropriate mathematical presentation of power system components. And we also conduct comprehensive load flow analysis, transient frost stability simulation and frequency response assessment to fully understand the effect of wind turbines viability on grid performance. Moving on to the objective of our project. So the first objective is to conduct a review of IEE power system standard, power system steady state stability analysis and renewable energy sources integration techniques. The second one is to develop a model of power system with wind turbine generated power system. The third one is to perform a steady state stability simulation of developed power system model. The fourth one is to investigate the impact of wind power system on steady state ability. And the last one is to propose a recommendation and mitigation measure to enhance the steady state stability of wind power system.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Syafika binti Sulaiman, which matrix card number DE220152, and I will present about the problem statement for our project. First is the global demand for electricity is rising, with increasing concern about greenhouse gas emissions. The shifting towards renewable energy sources like wind is crucial for sustainable energy solution. Wind energy offers environmental benefits and cost savings, but challenges grid stability and reliability. The variability in wind power generation leads to voltage fluctuations and grid instability. Environmental factors cause voltage fluctuations and power supply variability, which impacting grid stability and frequency. This fluctuation can disrupt grid stability and reliability, which affecting the electricity distribution. This project aims to analyze wind power system condition using mathematical model. This is to focus on enhancing grid stability during wind turbine integration through the comprehensive analysis. And lastly is to conduct comprehensive analysis such as load flow, stability simulation and also frequency response to improve power system stability during wind turbine integration. This analysis aims to identify and mitigate grid stability issues caused by the wind power variability. Next, I will present the scope of limitation for our project. First is the review of IEEE standards and techniques. We conduct a review of IEEE power system standards and techniques for steady-state stability and renewable energy integration, which limited to available literature and potentially excluding the latest proprietary advancement. The second one is model development. We also develop a simplified simulation model of a power system with wind turbine generated power systems using MATLAB or Simulink, which may not capture all real-world complexities. The third one is simulation of steady-state stability. We perform idealized steady-state stability simulations on the developed model under various conditions, which may not fully represent the real-world scenarios. The fourth one is the impact analysis. We analyze the impact of of wind power on system stability, which focusing on voltage and frequency based on simulated data that may not capture all real-world factors. And lastly, recommendation and mitigation measures. We propose theoretical recommendation and mitigation measures to enhance stability with integrated wind power, which requiring further validation and potentially not addressing all practical and economic constraints.
Hi, my name is Kuhin. My metric number is DE230141. Today I'll be presenting about the overall literature review of our project. So first, wind turbines and power system integration. The integration of wind turbines into power system introduce variability and uncertainty due to the intermittent nature of wind. Unlike conventional power plants, wind turbines generate power based on wind speed, which is inherently variable. The variability can impact voltage levels, power equality, and overall system stability. What is the impact on voltage stability? One is the connection of wind farms can lead to voltage fluctuations and potential instability if not properly managed. Second, the use of reactive power composition devices such as STATCOM static synchronous competitors has been proposed to mitigate these effects. Dynamic reactive power plant Dynamic reactive power control strategies can enhance voltage stability in systems with high wind power penetration. The influence on load flow patterns. The addition of wind turbines alters the traditional load flow patterns within power system. It is highlighted that the variability in wind power generation requires advanced load flow analysis techniques to accurately predict system behavior. Probabilistically, load flow methods, which account for the stochastic nature of wind, have been developed to provide more reliable results. Probabilistic load flow analysis. These methods use statistical distribution to model wind speed and power output, providing a more comprehensive assessment of system stability under varying conditions. The probabilistic load flow method involves solving the power flow equations multiple times with different input scenarios, typically generated using Monte Carlo simulations. Time series load flow analysis. Time series Time series analysis, which evaluates load flow over different time intervals, has also been employed to study the impact of wind turbines. This helps in understanding the temporal variations in power generation and load demand, thereby offering insights into potential stability issues. As for the mitigation strategies, first, advanced control systems. The development of advanced control systems for wind turbines, including pitch control and power electronic converters, has been pivotal. These systems enable better regulation of power output and reactive power support, enhancing overall system stability. Next, energy storage solutions. Energy storage technologies such as batteries and flywheels offer a means to buffer the variability of wind power. Studies demonstrate how energy storage can provide ancillary services such as frequency regulation and load leveling, thereby supporting load flow stability. That's all for me. Thank you very much.
Okay, right now I'm going to talk about the methodology. The impact of wind turbines on the load flow stability. Project focus on analyzing the stability of power system using the IEEE E14 bus system and the fast decoupled method. Detailed MATLAB simulation models various scenarios to observe the effect of the wind turbine on bus voltage, power flows, and stability margins. The fast decoupling method ensure efficiency load flow analysis. The study also examines transient stability and frequency response to understand the system reaction to disturbance. By automating simulation and validating results against benchmark studies, the project provides valuable insight into enhancing power system resilience and stability with integrate wind energy. Okay, now I'm gonna explain about the MATLAB coding for our project impact of wind turbine on low float stability. We implemented this method using MATLAB, and I will explain it later. First, we initialize the program with necessary command to clear previous data and start a timer for the performance measurement. Then we define the bus data, which include bus number, type, voltage, power generation, and load. Next, we define the line data, including the form and and to buses resistance, reactance, and admittance. Then we calculate the admittance matrix Y bus by iterating through the line data and computing the admittance, as you can see. Set the initial condition for voltage, magnitude, and angle, as well as power generation and load. After that, we iteratively solve the power flow equation until the solution converges within a specific tolerance. Finally, we display the result, including voltage magnitude, angles, and power values for each batch. So this code efficiently analyzes the impact of wind turbines on load flow stability using the fast decoupled load flow method. We initialize bus and line data, construct the Y bus matrix, solve the power flow equation literally, and analyze the result to understand the system stability. This approach help us integrate wind energy into the power system effectively. I think that's all for me. Thank you.
Assalamualaikum and hi, my name is Muhammad Fidaus bin Mazlan alias Faisal. My matrix number is DE220194. So, this is our result and discussion. Our group choose the IEE 14 bus system, and we decide to change the bus 9. So the initial value for the bus 9 is 29.5 milliwatt and 16.6 megavar. After that, the load has been increased to 100%, and the voltage per unit value at the bus 9 is we will record. So let's so we go to the next slide, and I will show you the table and the graph. So this is our result at the table and our graph. So this is the at the table. As you can see, the real power is 29.5 milliwatt and megawatt, and the reactive power is 16.6 megavar, and the voltage that we get is 1.034. And then the next one is 59 megawatt and 33.2 megavar, and the voltage that we get is 1.007. And then the next one is 118 megawatt and 66.4 megavar, and the voltage that we get is 0.944. And lastly is 236 megawatt and 132.8 megavar, and the the voltage is 0.0708. And then the system collapse when the voltage reach at 0.708 per unit. So this is our graph for the real power versus voltage per unit and the reactive power versus voltage per unit. Uh, As you can see at the graph, the the voltage per unit will decrease if the real power and the reactive power is increasing. So the power of load and the reactive power will affect the voltage per unit for the system. Okay, so we have been installed the wind turbine distributed generation WTDG at the bus stop 9, and we recorded the increasing of the voltage per unit. So as you can see in the table that we get is we increase from the 0 until 400. The first one is 0 and we get the voltage per unit is 0.708, and then we increase to another 50% and we get 0.788, and then 100% is 0.833, and 150% 0.864, and 200 is 0.886, and 250 is 0.901, and 300 is 0.910, and 350 is 0.914, and 400 0.913. So as you can see in the table, we increase from 0% until 350% of it rates capacity. The voltage also increase. However, at 400%, the voltage per unit decreased to 0.913 per unit. So from the table, the maximum voltage per unit that we obtain from the data, the maximum voltage per unit that we obtain from the data is 0.914 per unit. So this is our graph for the generated power versus voltage per unit. So in conclusion, our team of power system engineer is dedicated to developing strategies that ensure stability in power system during the integration of renewable energy source. With increasing electricity demand and the detrimental environmental impact of fossil fuel and natural gas dependency, transitioning to renewable energy is imperative. Renewable technologies, supported by government initiative, offer a cleaner and more sustainable solution. However, integrating this source presents stability challenges that require careful analysis and innovative solutions. By focusing on optimizing system parameters, enhancing control strategies, and addressing variability, we can achieve a resilient and stable power system that leverage the full benefits of renewable energy. That's all from our group. That's all from my group. And thank you. Assalamualaikum.